All right, this is Mr. Goom. Today we're going to start talking about the triangle midsegment theorem and a few more theorems that are properties of parallel lines that will help us to solve these missing sides and things like that a little easier. And the triangle midsegment theorem says that if you have two midsegments, so basically before we get started, let's just pretend we had a triangle here. I'll try to model it like that. A midsegment would say, a midsegment of this triangle would be from the midpoint here, the midpoint here. It divides it exactly up in half. The midsegment itself would look like that. Okay, and so I have this diagram here, and it is already pre-drawn. So that triangle has a midsegment that connects J to K, and J is exactly in between F and H, and K is exactly in between G and H. All right, and so we call it a midsegment. Okay, there would also be a midsegment halfway in between G connecting it to J, but in this particular diagram, there is no midsegment drawn, so I don't want to confuse anybody there. So the midsegment is the middle connecting the middle, connecting the middle. Okay, each of these would be midsegments. In this case specifically, we just had this one midsegment drawn. Now that midsegment has some properties about it. It says that each side is exactly equal. And it also says that the midsegment is guaranteed to be parallel to the other side. Okay, so the most important part of the midsegment is this one, or I guess the quickest and nicest trick is this guy right here. Okay, it says that they're parallel, but it also, there's a relationship here that it would make sense since there's two pieces that this length of the midsegment is half as long as the length of FG. So JK is exactly half the length of FG. So if FG was 8, the midsegment would be 4, no work required. You would know it's exactly half if this is a midsegment. You would know that it's parallel and it's exactly half of the other side, of its parallel side. All right, so I maybe would even illustrate this as if this side was 2x, this side would be x. Okay, and that's a property of midsegments, and the triangle midsegment theorem says that it's always that case. If you're looking at a midsegment, because both sides are exactly equal, this midsegment is exactly half the size of the parallel side. All right, so we're going to use that to our advantage here. Oops. When we're solving this next question. Okay. Now, I think you have more detailed directions than I do on my PowerPoint slide here, but basically what it says is that XY and XZ are midsegments. So XY and XZ are midsegments. And that tells me that this is divided up exactly into exact halves. And this is divided up into exact halves. If they're midsegments, it also tells me that these guys are exactly equal as well. All right, so we have these midsegments here. I could even draw another midsegment in from here to here as well. There's up to 3 midsegments on each triangle, but that one's not illustrated in the drawing. So let's just go ahead and kind of figure out what is XZ. XZ is represented by this guy right here. Okay. To find XZ, what we're going to do is we're going to use the triangle midsegment theorem. And it says that if I have this big triangle, RST, and I have its midsegment right here, it is guaranteed to be parallel to this guy. It's also guaranteed to be half as long as that one. Okay, so I'm looking at the big triangle, and I'm comparing it to its midsegment to its parallel side. Okay, the relationship there is this guy, this little XZ right here, is exactly half the length of RT. So let's write that down. XZ is 1/2 of RT. Okay, I know that because the triangle midsegment theorem promises me that since these are midsegments, they're parallel, and XZ is exactly half of RT. Well, in this case, 1/2 of 13 would be 6.5, or 6 1/2. However I decide to have you write it, 6 1/2. So right off the bat, I know XZ is 6 1/2. Okay, if I'm finding ST, all right, similarly, I'm looking for ST. because it's a mid-segment, I could say a couple different things. Now I'm going to go ahead and erase the diagram. So if you need to redraw a diagram or however you need to do it, okay, I want to show you which ones I'm comparing. Now I'm looking at our ST again, but I'm looking at this mid-segment. I'm promised that these are going to be equal, and I'm promised that this mid-segment is parallel to its parallel to this side that looks parallel to it, the one that's not being used and it's not included in the segment. So I'm going to compare that to this. So what I'm saying is if these are parallel and this is the mid-segment, then this is exactly half of this full length here. Okay, so if this little guy right here is 7, that means this guy right here must be 14. So that helps us to find ST because of the triangle midsegment theorem. So it's quick, really quick. It's going to take some practice, but I think we'll get it. 14 units. All right. So it's just trying really to figure out which triangles they're talking about. I'm talking about the big triangle and the midsegment here. So my two similar triangles are this guy and this guy on this problem. All right. Finally, ooh, we got an angle problem here. A little angle problem. It says we were trying to find the measure of angle RYX. The measure of angle RYX. So it looks like we're trying to find this guy right here. All right, we're trying to find that guy. If we know for sure that this is a midsegment, then I know that this guy is parallel to this guy. XZ is parallel to RT. So what I actually have here is, if I continued line in auxiliary style, I would have alternate interior angles here. So I would know that that angle is actually 124 degrees as well. So RYX is exactly the same as ZXY. The alternate interior angles, 124 degrees. All right, this is called the triangle midsegment theorem. We can find all these things quickly through the triangle midsegment theorem. All right, so I just want to reiterate one more time. I know it's annoying, but we're going to do it one more time. This guy is half the length of this guy if these are midsegments. This guy is guaranteed to be parallel to this guy if they're midsegments. If I continue these lines here, you'll see that my parallel lines have a transversal. This guy and this guy must also be equal. Oh, sorry, this guy must also be equal. Alternate exterior. And we have alternate interior angles as well. Okay, so there's a whole bunch of angles with those parallel lines that we know are congruent through the side or the corresponding or alternate interior, alternate exterior, those types of things. All right, well, let's take a look at another one here. It says find DE. So once again, we have another diagram here, and it appears to me that since these are exactly, this big triangle is split into exactly half pieces, that each of these is a midsegment. This guy is a midsegment, this guy is a midsegment. Let's try to use that to our advantage. So if we're trying to find DE, I can compare this guy, and I know that he is exactly half of the length of CA. So in this case, I'm comparing these similar triangles, and these are midsegments. I know that this guy is half of this whole length. So in this case, half of 15 is 7.5. Okay. DB, on the other hand, DB, where's DB at? Let's erase the diagram so I can get fresh perspective. DB is this little fella right here, from here to here. Okay, well, we know some things about DB. He's also equal to AD, which might help us. We're trying to find its length. So let's just see here. It appears to me that since this is a midsegment, that this guy is parallel to this guy, and this guy is half of the entire side here. Well, that's lucky for us because if this guy is half of this entire side, then I know that this must be 9.2 and this must be 9.2 if they are equal parts of the 18.4. So in that case, DB should equal 9.2. And finally, angle FED. FED. All right, angle FED. FED. Let's just see here. It appears to me as if FED, where can we go about solving for FED? If I have this mid-segment here, I know for sure it is parallel to this segment as well. These are parallel. And it looks to me like I have this transversal here. The alternate interior angles theorem says that if you have two parallel lines and you have this inside, this interior angle, its alternate is also the same measure. So in this case, angle FED would also equal 82 degrees. All right. If it helps you to draw that line out in parallel more, that might help too. Okay, so we're going to say this guy is 82 degrees as well. Proportional parts of parallel lines. If three or more parallel lines intersect two transversals, then they cut off the transversals proportionally. That sounds really confusing and long, but it's not near as bad as it seems. It says if these three lines are parallel, then AB compared to BC is also equal to EF compared to FG. It's very similar to the theorem we learned yesterday, okay, about the triangles and their parts here. We could say this guy compared to this guy is the same as this guy compared to this guy. Same exact thing. These lines are going to continuously, they're going to make a triangle eventually, these two transversals. So it's the same kind of deal, all right? If they're all parallel, they all have to be parallel at the same time. So AB compared to BC and EF compared to FG, those are going to be proportional as well. So if I look at this plot, it says frontage is the measurement of a property's boundary that runs along the side of a particular feature, such as a street, lake, ocean, or river. Find the ocean frontage from lot A to the nearest tenth of a yard. So we're looking for the frontage. This is the ocean. The frontage would be represented by this segment right here, this segment length. All right, and so what we have here is we're trying to use, since we have three parallel lines, these three parallel lines here, these transversals will eventually make a triangle. So I mean, even if you visualize a triangle that went on, okay, it's the same theorem that we were talking about yesterday. We know that if I compare 58 to 42, it should be the same, should be proportional to this distance compared to this distance. So that's what we're going to do. We're going to say 58 compared to 42 is equal to the unknown compared to 60. All right, now make sure we're not comparing sideways like this. That's not how we're doing it. Okay, these are both sides of the same triangle. We need parts of different triangles. The first triangle here, and the second triangle is the big one. Okay, so let's take a look here. I'm actually going to reduce this fraction. 29 over 21 equals x over 60. It'll just make my numbers a little easier to work with. And 29 times 60 1740 equals 21x, and then I'm going to divide by 21, and we'll see if that works out evenly. No, it doesn't, of course. So it does say to the nearest tenth of a yard, so let's go ahead and say 82.9. In this case, x equals 82.9. And we're finding the frontage, so yards is that distance, 82.9. All right, so it's just a comparison similar to that of yesterday's. Finally, we have something very similar to that as well. It says if your transversal is cutting through these parallel lines and it just so happens to be that AB and BC are the same exact length, it guarantees that any other transversal going through that also has the same length. So that guarantees me that EF and FG are also the same length. If I drew a transversal right there, I would know that these lengths are the same. Right there, I would know that these lengths and these lengths would be the same. Okay, so it only takes one transversal to have the same lengths in between the parallel lines to show that all the transversals have the same lengths between the two parallel lines. So let's finish up this last problem in class, and we'll go from there. That's it for today.